morning. In the last class we have seen how the thermodynamic potential relations for infinitesimal changes can be obtained using the Van-der-Waals diagram or chronic bond diagram. Today we can go into the applications of this Maxwell's equations, that is the TdS equations. There are three TdS equations, so we can go into the TdS equations. There are three TdS equations, so we can go one by one. The application means, earlier we have seen that it is very difficult to experimentally find the entropy values or the changing entropy values, but it is very easy to find experimentally the change of other thermodynamic coordinates, that is volume, temperature, pressure, etc., with respect to the change of any of these coordinates. So if whenever this dou s coming in the equation, we can replace dou s by dou t or dou s by dou p, etc. are coming into the equation. We can immediately replace that equation with the other experimentally obtained quantities using the Maxwell's equations. That is, we can replace the dou s variables, change in entropy variables with respect to some thermodynamic quantity with the experimentally obtained quantities. So for that, we can write the entropy as a function of T and P, then entropy as a function of T and P, then entropy as a function of P and P. So we will obtain three different TdS equations. So at first, we can obtain first TdS equation. For that, we can consider S as a function of T and V. Take S as a function of T and V. So immediately we can write ds is equal to dou s by dou t at V into dt plus dou s by dou v at t into d. Then multiply this equation by t, that is T ds equal to t into dou s by dou t at V into dt plus t into dou s by dou v at t into d. But we know that for a reversible process, TdS is equal to dq. This equation we have already derived. For an isochoric process, TdS equal to dq. So this one we can write as t into dou s by dou t at V. This is for reversible isochoric process. So this equation t into dou s by dou t at V can be written as, this is actually t into ds by dt, t into ds by dt at a constant volume, something like that. So we can immediately write this as dq by dt at a constant volume, that is nothing but the Cv. So we can rewrite this equation as TdS is equal to, this whole thing is Cv, that is Cv dt plus t into dou s by dou v at t into d. So here we have this equation dou s by dou v at t. This is actually the variable, we have the variable here as this entropy. This is entropy. So this quantity is very difficult to find experimentally. So we can replace that quantity, that dou s by dou v at t, that quantity, or that differential, that partial differential with some other variable, some other partial differential quantities using Maxwell's equation. We have the third Maxwell's relation. We have the third Maxwell relation as dou S by dou V at T is equal to dou P by dou T at V. So this S is this variable, this partial differentiation, this is very difficult to find out since it contains ds. So it is very easy to find out, that is dou P by dou T at constant volume. So we can replace this variable, this partial differentiation with respect to this one using this is the third Maxwell's relation. This is the third Maxwell relation. So we can write the TDS equation as TDS equal to CV dt plus T into dou P by dou T at V into D. This is the first TDS equation. This is the first TDS equation. That is TDS equal to CV dt plus T into dou P by dou T at V into dV. This is the first TDS equation. So there are different applications of this TDS equation. So we can write some applications, some usefulness for this first TDS equation. One is the heat transfer during an isothermal expansion of a van der Waals gas. Van der Waals gas is actually the real gases. So one application is this equation can be used to find the total heat transfer during an isothermal expansion of a van der Waals gas. Isothermal expansion from some initial volume Vi to a final volume Vf for a van der Waals gas. So for a van der Waals gas, for 1 mole of a van der Waals gas, we can write this equation. We can write the molar equation. That is, everything we have to write in small. That is T into ds. Ds is a molar. We can just write molar. This is for 1 mole equal to Cv for molar 1 mole dt plus T into dou P by dou T at V into dV. This is again for molar volume. For molar 1 mole, we can replace this equation as this one. So this S, M and Cv are the molar quantities. So the van der Waals equation, we can write the van der Waals equation as, we can write the molar van der Waals equation as P is equal to RT by V minus V. This is actually molar. I am writing the small letter like this. Minus A by P square. This is the molar volume, the same quantity, A by B square. So we can, this is the van der Waals equation. That is, this is for real gas. So ideal gas, these two quantities will goes to 0 like that. So here we can take a change, dou P by dou T at V. Dou P by dou T at V. What is dou P by dou T at V? Constant volume. Means this quantity will goes to 0. Here R by Dm by minus B. This quantity is a constant at constant volume. This is a constant. So R by V minus B into dou T by dou T, that is 1. Here this quantity, it is constant, so constant volume, so this total quantity is a constant, so the change will goes to 0. So dou P by dou T at V equal to R by V minus B. So from this equation we can write TDS equal to same thing dV. Since we are dealing this equation for isothermal process, this is for isothermal expansion, this dT can goes to 0. So we can write this equation as T into equal to, this will goes to 0. So T into R by V molar volume minus V into dV. So that this is small heat transferred for when 1 mole of a van der Waals gas is expanded isothermally. So this is the small quantity. So we can, this is actually TdS, which is actually the dQ value. So for the total change in the heat or the total heat transferred during an isothermal expansion of 1 mole of a van der Waals force is that Q is equal to, this we have to integrate. So this integration will leads to isothermal. So integral ds, that is T into S, that is the total heat transferred. So this is equal to T into integral some Vi molar volume Vi to some molar volume Vf R by Vm minus V into dV, which is equal to T into R into integral Vmi to Vfi dVm by Vm minus V. This will be a log quantity. So that Q is equal to T into R into ln Vm minus V from some Vmi to Vmf, which will be equal to T into R into ln Vmf minus V divided by, it is actually log this minus log of this value minus log of this value. So log A by B you will get. So this is Vmi minus V. This is actually heat. So the total heat transferred during an isothermal expansion of the van der Waals gas is given by the equation, that is for 1 mole is given by the equation Q is equal to Tr into or RT into ln Vm. This is for representation of molar volume F minus V, Vmf minus V. This is Vmi, this is actually molar volume, initial molar volume minus this B quantity. So you will get this heat transferred, these all things are experimentally obtained quantities. So you can obtain this equation from the first TdS equation. This is for n mole. So for 1 mole, we find 1 mole of a van der Waals, you will get this equation. The total heat exchanged or transferred during an isothermal expansion of a van der Waals gas is given by this equation. So this is one of the application of this first TdS equation. The first TdS equation is the S is depending upon V and T. So from that we have obtained this relation. So we will obtain this first TdS equation. So the application of the first TdS equation.